Hello class, welcome to Stat 1200. I am your instructor William Buellman, and today we are covering section 5.2, the binomial distribution. Our objectives for today are to be able to determine whether a random variable is binomial, determine the probability distribution of a binomial random variable, compute binomial probabilities, and to compute the mean and variance of binomial random variables. Suppose that your favorite fast food chain is giving away a coupon with every purchase of a meal. 20% of those coupons entitle you to a free hamburger, and the rest of them say better luck next time. 10 of you order lunch at this restaurant. Suppose we want to know the probability that 3 people win a free hamburger. In general, if we let X be the number of people out of 10 that win a free hamburger, what is the probability distribution of X? In this section, we will learn that X has a distribution called the binomial distribution, which is one of the most useful probability distributions. In the problem just described, each time we examine a coupon, we call it a trial. So there are 10 trials. When a coupon is good for a free hamburger, we call it a success. The random variable X represents the number of successes in 10 trials. A random variable that represents the number of successes in a series of trials has a probability distribution called the binomial distribution. The conditions are as follows. A fixed number of trials are conducted, so that means the amount is fixed. You can't have unlimited trials. There are 2 possible outcomes for each trial. One is success, and the other is failure. So you can only have 2 things, either success or failure. There cannot be a third option. The probability of success is the same on each trial. So the probability of success cannot change from trial to trial. The trials are independent. Which means one trial does not affect the outcome of other trials. The random variable X represents the number of successes that occur. In our notation, we're going to go N is equal to number of trials. P is going to be equal to the probability of success. Example 1. A fair coin is tossed 10 times. Let X be the number of times the coin lands heads. Is this a binomial experiment? So this is a binomial experiment. There is a fixed number of trials, 10. There's 2 possible outcomes, heads or not heads, and we want to know the number of heads. So we have success, which is heads, and failure, which is not heads. And are the trials independent? Yes, because what if the first coin flip comes up heads, it's still the same 50-50 chance that the second coin flip is heads or not heads. So each trial is independent. Thus, we have a binomial experiment. 5 basketball players each attempt a free throw. Let X be the number of free throws made. Is this a binomial experiment? This is not a binomial experiment, and the reason why is the probability of success making the free throw from one player to the next player is not the same. If you look at professional basketball players, they all have different free throw percentage makes, so it's not fair to assume that the probability of success for each trial is going to be the same, and since the probability of success is not constant, it is not a binomial experiment. Example 3. 10 cards are in a box. 5 are red, 5 are green. 3 of the cards are drawn at random. Let x be the number of red cards drawn. Is this a binomial experiment? This is not a binomial experiment. So let's suppose the first card we draw is red. The probability of getting that first card as red is 0.5. Now let's say we draw the second card and it's red. The probability that the second card is red, given that we know the first card is red, is 0.444. So now we don't have the same probability of success, and our trials are not independent because what happens on the first trial affects the probability on the second trial, and since they're not independent, it is not a binomial experiment. Consider the binomial experiment of tossing 3 times a biased coin that has a probability of 0.6 of coming up heads. Let x be the number of heads that come up. If we want to compute the probability of 2, the probability that exactly 2 of the tosses are heads, there are 3 arrangements of 2 heads in 3 tosses. We could get heads, heads, tails, heads, tails, heads, or tails, heads, heads. The probability of heads, heads, tails is the probability of heads, heads, tails, which is equal to 0.6 times 0.6 times 0.4, which is equal to 0.6 squared times 0.4. Similarly, we find that the probability of heads, tails, heads is equal to tails, heads, heads, which is also equal to 0.6 squared times 0.4. Now that the probability of 2 heads is equal to the probability of heads, heads, tails, or heads, tails, heads, or tails, heads, heads, is equal to 3 times 0.6 squared times 0.4 by the addition rule. Examining this result, we see that the number 3 represents the number of arrangements of 2 successes, heads in this case, and 1 failure, tails. In general, this number will be the number of arrangements of x successes in n trials, which is n combination x, which we've seen before in section 4.4, the combinations. The number 0.6 is the success probability p, which has an exponent of 2. The number of successes x. The number 0.4 is the failure probability, which is 1 minus p, which has an exponent of 1, which is the number of failures n minus x. In general, for a binomial random variable x, the probability of x is equal to n combination x times p to the x power times 1 minus p to the n minus x power. The possible values of the random variable x are 0, 1, all the way to n. So what this is saying is n choose x times the probability of success raised to the x power times the probability of failure raised to the n minus x power. Example 4, hand computation. The Peru Research Center reported in a recent year that approximately 30% of U.S. adults own a tablet computer such as an iPad, Samsung Galaxy Tab, or Kindle Fire. Suppose a simple random sample of 15 people is taken. Use the binomial probability distribution to find the following probabilities. Find the probability that exactly 4 of the sampled people own a tablet computer. Find the probability that fewer than 3 of the people own a tablet computer. Find the probability that more than 1 owns a tablet computer. And find the probability that the number of people who own a tablet computer is between 1 and 4 inclusive, which means 1 and 4 are included. Note that n equals 15 here. We have 15 trials, and the probability of success is 0.3. So the first thing we need to do is find the probability that exactly 4 of the sampled people own a tablet computer. We use the binomial probability distribution with x equaling 4, n equaling 15, and p equaling 0.3. So the probability of 4 is 15 combination 4 times 0.3 to the 4th power times 1 minus 0.3 to the 15 minus 4 power. which is equal to 15 factorial over 4 factorial, 15 minus 4 factorial, 0.3 to the 4th power times 0.7 to the 11th power. If we do this whole factorial, we get 1,365 times 0.3 to the 4th power times 0.7 to the 11th power, which when we multiply that out, we get 0.219 if we round to 3 decimal places. So number 2, we still have the n equals 15 and p equals 0.3, but this time we have to find the probability that fewer than 3 of the people own a tablet. The possible numbers for fewer than 3, so fewer means 3 is not included, are 0, 1, and 2. So the probability of 0, 1, or 2 is equal to 15, choose 0, times 0.3 to the 0 power times 1 minus 0.3 to the 15 minus 0 power plus, so that's the probability of 0. Now we have to do the probability of 1. 15, choose 1, times 0.3 to the 1 power times 1 minus 0.3 to the 15 minus 1 power. So that's the probability of 1. Now plus the probability of 2, which is 15, choose 2, times 0.3 to the 2nd power times 1 minus 0.3 to the 15 minus 2 power, which if we do each one of those, we get 0.0047 for the probability of 0, plus 0.0305 for the probability of 1, plus 0.0916 for the probability of 2, and when we sum that up, we get the probability of 0 or 1 or 2 is equal to 0.127. 3. Find the probability that more than one person owns a tablet. For this, we're going to use the rule of complements. The complement of more than 1 is 1 or fewer, or equivalently 0 or 1. The probability of 0 or 1 is equal to the probability of 0 plus the probability of 1. So again, 15 combination 0 times 0.3 to the 0 power times 1 minus 0.3 to the 15 minus 0 power, that's the probability of 0, plus 15, choose 1, times 0.3 to the 1 power times 1 minus 0.3 to the 15 minus 1 power, that's the probability of 1, which we already found was 0.0047 for probability of 0 plus 0.0305 for the probability of 1, which when we add those together, we get 0.035. Now use the rule of complements. So remember, that's 1 minus the probability of 0 or 1, which is equal to 1 minus 0.035, which is equal to 0.965. So the probability of more than one person owning a tablet is 0.965. 4. Find the probability that the number of people who own a tablet is between 1 and 4 inclusive. Between 1 and 4 inclusive means 1, 2, 3, or 4. So now I'm going to write down the probability of each one of those. So 15, choose 1, times 0.3 to the 1 power, 1 minus 0.3 to the 15 minus 1 power, plus 15, choose 2, 0.3 to the 2nd, 1 minus 0.3 to the 15 minus 2, plus 15, choose 3, 0.3 to the 3rd, 1 minus 0.3 to the 15 minus 3, plus 15, choose 4, 0.3 to the 4th, 1 minus 0.3 to to the 15 minus 4, which each one of those is 0.0305 plus 0.0916 plus 0.1700 plus 0.2186. When we sum those up, we get 0.511. So we're going to do example 4 over again, but this time we're going to use tables, because as you saw before, doing it by hand can be complicated. It's time consuming, but you still need to know it because you may be asked to do it by hand, and if I ask you to do it by hand, I expect you to show the by hand work, not just give me the answer. So you need to be able to do it by hand. I'm going to show you tables next. So same problem using the tables in your book. This problem, we're using the tables in our book. We're looking at table A1, and what we do is you need to go look through the tables till you find the correct n, which in our case is 15. So now we know we're using the right table. And then you need to look for your number of successes, which in our case is 4. So you go down to x equals 4 right here, and then you look at what your probability is, which is 0.3, and then we go where those numbers come together, and that will give us the probability of 4, which is 0.219. So we just use the table, look it up. These won't always be exactly the same as the by hand calculations because there might be a slight bit of rounding difference. Similarly, we find the table where n equals 15, which we have here, and then we're interested in 0, 1, or 2. So here's our x's, 0, 1, and 2. And then we find the probability that goes with that. And then we read these values right here. So the probability of 0 was 0.005. The probability of 1 is 0.031. And the probability of 2 is equal to 0.092, which when we add those up, we get 0.128. So number 3, find the probability that more than 1. So I'm going to remind you we're going to use the complement rule. So we want to find 0 and 1. We need to find what is the probability of 0 or 1, which if we look right here, we have the probability of 0 is 0.005, and the probability of 1 is 0.031, the highlighted in blue up there. So we get that is equal to 0.036. So now we use the complement rule and we get the probability of more than 1. Is equal to 1 minus the probability of 0 or 1, which is equal to 1 minus 0.036, which is equal to 0.964. And finally, we have the probability of between 1 and 4 inclusive, which was 1 or 2 or 3 or 4, which at this point we know how to read the tables. We're just looking at these right here. So we have 0.031 plus 0.092 plus 0.170 plus 0.219. And when we add that up, we get 0.511. You need to be comfortable doing both by hand and by table method. You could be asked either one on a quiz to either do it by hand or by table or on an exam. And if you are asked to do it by hand, you have to show the by hand computations. If you just spit out the answers and say, oh, from table A1, it will be incorrect. So you guys need to be comfortable doing it both by hand and by tables, and telling me if I ask you to use a table, telling me what n you used, what x you used, what p you used, and where you got the information from. And if you use tables, only use the ones from the book. Do not get them from outside sources. Let x be a binomial random variable with n trials and success probability p. Then the mean of x is just n times p. The variance of x is n times p times 1 minus p. The standard deviation of x is the square root of n times p times 1 minus p. So standard deviation is still the square root of the variance. You can see here that calculating the mean and the variance, long as we know n and p, is very quick because all it is for the mean is n times p, and for the variance, n times p times 1 minus p. Example 5. The probability that a new car of a certain model will require repairs during the warranty period is 0.05. A particular dealership sells 68 such cars. Let x be the number that will require repairs during the warranty period. Find the mean and standard deviation of x. First, we're going to write down the information that we have. We know n is equal to 68. There were 68 cars sold. And the probability of success that something needs to get worked on is going to be equal to 0.05. So if we look back, our formula for mean, mu of x, is equal to n times p, which is equal to 68 times 0.05, which is equal to 3.4. So our mean is 3.4 cars. The standard deviation, sigma of x, is equal to the square root of n times p times 1 minus p, which is equal to the square root of 68 times 0.05 times 1 minus 0.05, which is equal to 1.797. So the standard deviation for this problem is 1.797 cars.